Could smashing atoms together accidentally unlock infinite riches? We've all heard of lead into gold, the alchemist's ultimate dream. Well, it seems physicists at CERN, with their giant Large Hadron Collider, might have just stumbled upon something that sounds suspiciously like it. But is it the breakthrough we've all been waiting for? Or is there a catch bigger than the collider itself? Just this month, May 7th, 2025, a paper hit the press from the ALICE experiment at CERN. They weren't looking for gold. They were smashing lead ions together at nearly the speed of light. You know, typical Tuesday at CERN. Usually these collisions are head-on, creating a fiery soup of particles. But sometimes these lead nuclei just miss. A near miss, an ultra-peripheral collision, they call it. And in these fleeting glances, something incredible happens. Imagine two lead nuclei, each packed with 82 protons, whizzing past each other. They don't touch, but their electromagnetic fields, super compressed and a million times stronger than lightning, slam into each other. This jolt can literally knock protons out of the nucleus. Knock out one proton, and lead becomes thallium. Knock out two, it's mercury. But what if you knock out three? 82 minus 3 is 79. And what element has 79 protons? You guessed it, gold. Now, scientists have suspected this kind of electromagnetic dissociation could happen. There were even hints back in 2002 and 2004 at a smaller CERN accelerator. But the ALICE team just published the first systematic detection and quantification of this. They actually caught the ejected protons and neutrons using special detectors, confirming that lead was indeed transforming. And yes, they counted events where exactly 3 protons got booted out, creating bona fide gold nuclei. So how much gold are we talking? The numbers are interesting. At its peak, the ALICE experiment was seeing about 89,000 gold nuclei created per second. 89,000. That sounds like a gold factory, right? An infinite money glitch unlocked by particle physics. Before you remortgage your house to build a mini collider in your backyard, there's a tiny subatomic catch. These newly minted gold nuclei are so energetic, so hyped up from their creation, that they exist for only a fraction of a microsecond before they smash into something and disintegrate. Poof, gone, ephemeral riches. So while the alchemist's dream has technically come true, the LHC isn't about to flood the market. During its entire run-to operations, from 2015 to 2018, all the LHC experiments combined are estimated to have made about 29 picograms of gold. That's 29 trillionths of a gram. A single grain of salt is billions of times heavier. To make just 1 gram of this fleeting gold at 89,000 atoms per second, you'd need to run the LHC for about 3.5 billion years. Given the $5 billion price tag for the LHC and its hefty electricity bill, this isn't exactly a profitable venture. It's less a gold mine and more a gold whisper. But here's where it gets truly fascinating. Why is this accidental alchemy even important if it's not making us rich? Well, this new data is incredibly valuable for understanding the forces at play. The ALICE results were compared to a leading model called RELDIS for events where no protons were lost or 3 were lost, making our gold. The model matched pretty well, but for 1 or 2 proton losses, making thallium or mercury, the model actually underestimated how often it happened by about 17 to 25%. Nature, it seems, is a bit more eager to knock out 1 or 2 protons than our theories predicted. This kind of discrepancy is gold for physicists, not the shiny kind, but the kind that helps refine their understanding and improve their models. And there are practical implications too. These near-miss collisions, where nuclei lose protons and change identity, aren't just a curiosity. They contribute to beam losses in the LHC. The transmuted nuclei drift out of the beam, hit the machine's hardware, and create background radiation. Understanding this process better, thanks to ALICE's measurements, helps engineers design and operate colliders more safely and efficiently. So the physicist's nuisance is actually a key to better big science. This isn't the first time scientists have made gold. Back in 1980, Nobel laureate Glenn Seaborg did it by smashing carbon and neon into bismuth, knocking off protons. He famously noted it would cost about $250 an ounce. The principle is the same. Change the number of protons, change the element. What Alice has done is observe this happening with unprecedented precision in a collider, using just the electromagnetic kiss of two near-miss lead ions. It's a testament to how far we've come, from ancient alchemists stirring potions to scientists manipulating the very heart of matter with fields of pure energy. So, what's next? These findings open up new questions. How far can we push these transformations? Could we knock out 4 protons from lead to make platinum? The chances drop dramatically with each proton, but who knows what future, more powerful colliders might see. And these detailed measurements of how nuclei break apart under electromagnetic stress also help astrophysicists. After all, nature performs its own alchemy in exploding stars, in neutron-star mergers, forging the gold we find on Earth. Understanding nuclear responses here helps us understand them out there. There's even a faint echo of this research in an entirely different field: nuclear waste management. Scientists are exploring using accelerators to transmute long-lived radioactive waste into more stable, less harmful substances. Different process, sure, but the core idea of using particle beams to change problematic isotopes is there, so CERN turned lead into gold. Not an infinite money glitch, but an invaluable insight. It's a beautiful reminder that sometimes the most profound discoveries are made when you're looking for something else entirely. The universe, it seems, still has plenty of elegant tricks up its sleeve. What impossible thing will we understand next, just by looking closely enough? Stay curious, and maybe we'll find out together in the next deep dive.